Good afternoon, everybody. I'd like to thank you all for coming out to this month's Explore session. My name is Dr. Andrew Flewelling, and I'm the research project facilitator for Horizon Health Network. My role primarily is to work with various learners across our health authority, particularly medical residents, medical students, pharmacy residents, and helping them with various aspects of the methodology around their research projects. Today, I'm going to talk about some considerations that should be taken into account following the analysis of your study data. I should note that this presentation focuses on quantitative data analysis and will not cover qualitative research. So first thing I'd like to say before getting into my talk is I'm not a statistician. I'm a researcher that uses statistics. So I'd like to note that before we begin. My background is natural products chemistry, and my experience lies in fundamental research. So my background and area of expertise is identifying new antimicrobial drug leads from microorganisms. I'd also like to point out that much of the content that's being discussed throughout the presentation are current topics of discussion with many opinions in the literature. So my goal here is to present some of the more common topics for your consideration. So to give an idea of why I'm giving this talk, my research background is one which I would consider falls under fairly black and white analysis and interpretation approach. So for my research, I would say, the microorganism is this species. The antibiotic has this chemical structure. But one thing I've noticed as I've moved to a clinical research focus is that while some cases the results can be clear, there also requires a lot of interpretation, and it isn't always agreed upon how data should be interpreted and how the results should be interpreted. So I might look and read through a paper, and someone else might, and we may have different thoughts and take different things away from a particular study. So to lead into the talk, things I won't be talking about, I'm not going to talk about which test to use. Do I have a large enough sample size? How do I prepare my data ahead of analysis? Now, this presentation is really about after you get your results from a program like SPSS or R or STATA. So just to step back, before we can discuss results, though, I should cover some background points. There are a number of analyses that might be appropriate for your study, which can depend on the design and the data being collected. Some analyses are descriptive, reporting perhaps the mean and standard deviation of the data, or detailing the frequency and percentage of an outcome. Or you might be trying to identify correlations between variables, obtaining a statistic like Pearson's R to detail the association. If you're looking at comparing two or more groups, analyses like the chi-square test, a t-test, or ANOVA are likely relevant to your study. And lastly, if you're looking to predict an outcome or identify variables associated with your outcome, regressions, linear or logistic, are typical analyses that would be performed. So, I'd like to also note that not all statistical tests fall into these four categories, but they typically cover much of what is performed and would be encountered in the literature. So when you run your statistical analyses, ultimately what you're doing is null hypothesis significance testing. So null hypothesis significance testing is the development and testing of hypotheses by selecting a threshold or limit, which we would call an alpha level, and creating alternative and null hypotheses and evaluating your obtained study results to decide whether or not to reject your null hypothesis. An alternative hypothesis is some claim that an independent variable is the cause of an observed effect. If you're looking at differences in age between two groups, you would be hypothesizing that there is a difference, or one group has a greater age than another group. The null hypothesis in this case is the counterpart to the alternative hypothesis, so that you'd be hypothesizing that there is no difference. So what do we use to draw our conclusions? Most likely, we're using a p-value and an alpha level. P-value represents the probability of obtaining a result equal to or greater than the one observed in the study when the null hypothesis is correct. It indicates the degree to which the data conforms to the pattern that's predicted by our null hypothesis, and it's assuming that our null hypothesis is true. Our alpha level is the threshold that we've selected ahead of time when performing our null hypothesis significance testing, and it's something that typically, conventionally, in the literature, it's been set to 0.05 or 5%. So then we can compare our obtained p-value for our analysis to our threshold level, our alpha, in order to identify whether there's a statistically significant result, where a p-value less than our alpha level would result in us rejecting our null hypothesis. So for the rest of the presentation from this point, I'll break down obtaining a p-value less than or greater than an alpha level, 0.05 for this presentation, and some considerations for obtaining each of these outcomes. So consider an analysis of your study data, and upon looking at the results output from your stats package like SPSS or Stata or R, you obtain a p-value less than 0.05. So when it comes to your study, what does this mean? And I'm going to give some examples for a few different tests, and I was going to give some medical examples, but they all seemed, when I was developing them, to relate back to COVID-19. So I pivoted away from that, and they all ended up relating to cars. So from now on, a lot of the examples I'm going to give are related to cars. So let's say your study was investigating associations between having a red car and getting a speeding ticket. You'd run a chi-square test, and you'd be working with a null hypothesis where you'd be hypothesizing that there's no association between the color of your car and getting a speeding ticket. So if you obtain a p-value less than 0.05, you're rejecting that null hypothesis, and you're able to conclude that there is an association between having a red car and getting a speeding ticket. And you can look into your data a little bit more to see whether there's a greater frequency of tickets with a red car or not. Moving on from that, if we're looking at a t-test, we're investigating differences in fuel economy between two car models. Our null hypothesis, again, in this case, would be that there is no difference in fuel economy. A p-value less than 0.05 in this case, you'd be concluding that you'd be rejecting your null hypothesis and being able to conclude that there is a difference in fuel economy. And again, you can look back at your data and get some information about which car model would have the greater fuel economy. Looking at correlations, maybe you're looking at an association between the cost of a car and the salary of the buyer when you're purchasing a new vehicle. Your null hypothesis, again, there is no association between these two variables. And with a p-value less than 0.05, you would likely conclude that there is an association between the cost and the salary. And you can look at something like Pearson's R to give some information as to the direction or the strength of the association. And lastly, perhaps you're trying to see which factors are associated with someone's choice in buying a vehicle. You want to see whether cost, style, mileage, various features are associated with the buyer's choice in the vehicle. A p-value less than 0.05 for each of these different factors would give you some information about which factors are indeed associated with the choice of the vehicle. And you can look at things, if you're looking at logistic regression, you could look at odds ratios to give some information about the importance of each of these variables. So this is just a quick and generic overview of p less than 0.05 for several types of analyses, but this is generally how you would proceed with null hypothesis significance testing that rejects a null hypothesis. But with that in mind, there are some considerations that I'll comment on now in relation to situations where your p-value is less than 0.05. And my main thought for any analysis is, does this make sense? First of all, have you looked at the data? What does the data look like? Have you plotted the data? to get some sense of the distribution, outliers, things like that. Now, this is something that you would typically do before analysis, but I would recommend this as well after analysis to really get a sense and understanding of your data in relation to what the statistical analysis is telling you. Another thing is, could your results be due to a type 1 statistical error, which I'll talk about in a minute? Or have you thought about giving or reporting the effect size for your analysis? So the type 1 error in statistics is the rejecting of the null hypothesis when the null hypothesis is true. So this is what we would consider a false positive situation. If we think back to some of the car examples, you're looking at fuel economy, and you say that there is no difference between these two groups, but in fact there is. So the two cars have different fuel economies. The chance of committing a type 1 error is tied to the alpha level that you've chosen for your analyses. So by choosing a suitable alpha level, you can restrict your chance of a type 1 error. Another thing to consider when obtaining significant results during your analyses is that you may be committing type 1 errors just due to the number of comparisons being made on the data. We know that each analysis we perform comes with a chance of committing a type 1 error. That's our alpha level, and we try to limit that. But as you perform more and more analyses on the same data, you are in a sense compounding the chance of those type 1 errors. So it brings up this issue of multiple comparisons in your data set. So consider you have an outcome of interest, again, difference in fuel economy. And from your data set, you're interested in seeing if the differences is a result of the weight of the vehicle, the tire type, the make, the model, the class, and just about any other feature that you can think of related to a car. So as you perform more and more comparisons on the same data, you're increasing your likelihood of committing a type 1 error, where you're potentially rejecting a null hypothesis when it's actually true. And the rate of performing this error can be quite high, even with just a few comparisons. So my colleague Donaldo Canales calculated in 2019, the impact of multiple comparisons on the probability of committing a type 1 error, and he put this into an Excel sheet and provided that to me. So I adapted this into a graph just to illustrate this impact of multiple comparisons. If you were to compare, if you were to have 5 comparisons and you're studying on your data, your probability of committing at least one type 1 error with a p-value of, or with an alpha level of 0.05 is over 20%. As we move up to 15 comparisons, the probability of at least one type 1 error is now over 50%. And as the number of comparisons increases, the probability of at least one type 1 error approaches 100%. At 50 comparisons, we're over 90% chance of committing at least one type 1 error with the data. So there are ways, though, that you can control this error. My first recommendation for controlling your chance of committing a type 1 error would be to develop an analysis plan based on theory, not developing protocol and data analysis plan based around trying to compare every feature related to your outcome of interest. Now, with that in mind, though, there are several techniques available for controlling type 1 error after your analyses. I'll present 2, but you should also note that there are far more than these 2, and the use of a technique might be situation dependent. So one popular method is the Bonferroni correction. So this method involves dividing your alpha level, that threshold for determining significance, by the number of analyses being performed on your data. So as the rate of committing a type 1 error is tied to alpha, this controls the type 1 error by reducing your alpha level for testing. So if you start off with an alpha level of 0.05 and you perform 10 comparisons, then your new alpha level is now 0.005. So it's a really effective method, but some consider it to be very strict and very conservative, and some suggest it may actually overcorrect in the direction of another error. So you actually may miss some level of significance for some of your analyses. One method that I use and have used in the past is the Benjamini-Hochberg correction. This method is less conservative than the Bonferroni correction, and it's based on a false discovery rate that you set in order to limit the chances of committing a type 1 error. So you're essentially acknowledging that some degree of type 1 error is possible, but by using a predetermined false discovery rate, you're limiting that error to the rate that you've set. So I consider it to be a pretty good balance between not correcting for multiple comparisons and potentially being overly conservative with something like the Bonferroni correction. So my other consideration for situations where your p is less than 0.05 would be to report the effect size and its accompanying 95% confidence intervals associated with the measure. So effect sizes give some sense of the magnitude of the effect being observed and can provide context to the association between two variables or how different two measures are. There are many forms of effect sizes and each are dependent on the analysis being performed. I've listed some of the common effect sizes here, and it might seem like a lot, but the choice of the effect size follows along with the test that you've used. So if you run a chi-square test, you would report Cramer's V for the effect size for that data. If you run a t-test, you'd use Cohen's d. So there are also established guidelines available for you to use to try and interpret what is a small effect size, what's a medium effect size, what's a large effect for each of these different effect sizes and different measures that we have. So the importance of effect sizes can be seen in this table adapted from Kim in 2015. So there's 3 examples presented here that detail analyses given different sample sizes, different differences between 2 groups. And if we look at example 1, so we can see that there's a before measure and an after measure, and there's a difference in this value of 3, whatever they're measuring, and they get 145 before, 142 after. They get a difference between those 2 groups of 3, and they have a sample size of 100. They run a t-test and they get a p-value of 0.382. So that's greater than our alpha level of 0.05, our threshold. So we would conclude that there is no statistical significance, and these groups before and after are not different. We can also look at the effect size, so giving some context to that difference, and we can get a Cohen's d. So Cohen's d, the interpretation of that falls around, if we get a value of 0.2, that would be considered a small effect. Value of 0.5, that would be a medium effect. And a value of 0.8 would be a large effect. So for example 1, there's a Cohen's d of an effect size of 0.03. So this would be very, very, very small, almost insignificant difference between these 2 groups. So yeah, we have an example where we have a non-significant test based on a t-test, for example, and a Cohen's d, an effect size that's very, very small. In our second example, we have the same difference between our 2 groups, but we've increased our sample size to 10,000. In this case, we now obtain a p-value that is 0.001, which is quite a bit smaller than our alpha level. So we would then conclude that there is a difference between these 2 groups. And really the driving factor of this is our much larger sample size. But when we look at our effect size, we have the same effect size. Cohen's d is independent of our sample size. So we might now have a situation where we can conclude from our statistical analysis that there's a difference between these 2 groups, but the context for that difference is still the same as before. It's still a very, very, very small difference. We move on to example 3. There's now a much larger difference between the 2 groups, but we've gone back down to our original sample size of 100. In this case, we get the same p-value, 0.001 as example 2, but now when we calculate Cohen's d, a standardized mean difference, the effect size is much larger than before. It would actually fall somewhere from a small effect to a medium effect. So we can see if we only performed our statistical analysis and didn't report an effect size, between examples 1 and 2, we would say that in one case, there's a difference between the groups, and in the other case, there is no difference, but we haven't given any context to that. Between examples 2 and 3, we would say that they both are statistically significant. Both cases, we have difference between the groups, but by looking at our effect size, we can see that the difference is actually much greater in one example than the other. So effect sizes are important for giving information beyond the p-value related to the magnitude of the effect being seen. So just to summarize that section, things to think about. Do your results make sense? Have you considered type 1 error? Have you reported your effect size? These are all important things when you have cases where your p-value from your analysis is less than 0.05. So perhaps you ran the same analyses that I mentioned before, all the different ones about cars. But in this case, your analyses return a p-value greater than 0.05. So you might be thinking, now what? There's probably many things that are going through your head at this point. But again, my first thought is, does this make sense? And it's for the same reasons as before. You want to be comfortable with your data and how that relates to the outcome of your analyses. And two considerations that I have for this presentation are related to power and sample size. And the first is the type 2 error. So type 2 error is retaining a situation where you retain the null hypothesis when the null hypothesis is in fact false. So this is considered a false and negative situation. So what we're saying, if we go back to this fuel economy example, you're saying, there is no difference between these two vehicles in their fuel economy when in fact there is. So statistical power is tied to your type 2 error, and power is the ability to detect an effect if one is actually present. I'm not going to go into further detail about power. We recently, actually in our last Explore session, had a full talk devoted to power analyses, but it is absolutely something that you should consider when interpreting your results, especially if you didn't perform power analyses when planning your study. So there's a really great importance for type 1 and type 2 errors. These can have serious impacts on your results, especially when you get to the point of trying to communicate the results from your study to your peers. You may be concluding in one direction when actually it's in the other direction. So with that in mind, power and type 2 error can extend to the next consideration that I have for you. So what if my p-value is quite close to my alpha level, to that threshold of 0.05? Am I trending towards significance with my data and results if I get a slightly larger sample size? So this brings me to the topic related to the title of my presentation, and really was something that gave me some inspiration for giving this talk. So statements related towards trending towards significance come up regularly in the literature when p-values are close or even not close to 0.05. The statements come in many forms, but should always be treated with caution, or in my opinion, completely ignored. And I do have some examples. There was a great blog post from some time ago that summarized a number of different statements related to trending towards significance and the p-values that were used. So one paper said only slightly missed the significance level, and they had a p-value of 0.0556. Perceivable statistical significance with a p-value of 0.0501. It was roughly significant when their p-value was greater than 0.1. Slightly failed to reach statistical significance, p-value of 0.06. Tantalizingly close to significance, 0.1. Technically not significant, p equals 0.06. Teetering on the brink of significance, tentatively not significant, very closely brushed the limit of significance. So there's a lot of these statements that are very misleading and are situations where people are trying to interpret their data as well as they can, but really are being misleading in the process that they're doing this. So, my question then is, as someone who's fairly recently moved into clinical research and away from fundamental research is, why do we think that way? Is more better when it comes to statistical analyses if I increase my sample size? And will I end up with a more significant result? My power analysis suggests that that more people reduces my chance of a type 2 error by increasing the power of my study. So having more data for my analysis must always lower my p-value. If, by that very thought, then I must be trending towards some statistical significance. And if I'm really close to my alpha level. So this very thought was challenged by Wood and others in 2014. And I'll present some of their data here by asking, what happens if we double our sample size? What if we had 100 participants, analyzed our data, got a p-value, realized that it wasn't below 0.05, but it was close, then got another 100 participants, added them in, and reanalyzed the data? Would we always end up with a p-value smaller than what we started with? If not, how often do we obtain a larger p-value? So Wood and others presented 3 scenarios related to sample sizes and their impact on analysis of the data, and I'll present them here. So the first scenario they give is related to the percent of time that a p-value would become larger, so less significant, if you doubled your data for the analysis. So what this graph is showing here is on the bottom, on the x-axis, we've got current p-values. So when you only had the original 100 participants in your study, you ran your statistical analysis and you got p-value. That's what the x-axis is showing. And on the y-axis, we're seeing the percent of times that our p-value would become less significant. So moving away from 0.05 and becoming larger. So just to provide one example here, I've highlighted a situation where you had 100 participants, you ran your analysis, you got a p-value of 0.06, something that's in the realm of many of these statements that are in the literature. And what Wood and others found is that about 1 in 5 times, 20% of the time, if you doubled your sample size, you would end up with a larger p-value than what you started with. If you did this many, many, many times. So yeah, 1 in 5 times our p-value would not be expected to be trending towards significance. Continuing on, they then presented data related to obtaining a non-significant result on doubling the data in the analysis. So the graph here is showing the same information as before, but this is not related to your initial p-value becoming larger or smaller. It's just whether it would be bigger or smaller than our alpha level, bigger or smaller than 0.05. What they found is if your first analysis had resulted with a p-value of 0.06, about a quarter of the time, you would still get a non-significant result. We can see here that if you started with a much smaller p-value, then that percent of time is much smaller and it moves upwards as your initial p-value gets larger. But lastly, they also presented something not related to increasing your sample size and adding it to the original data. But what if you had 100 participants in your study and you went out and got a new sample of 100 different participants and analyzed that data independently to the first analysis? If you started out and your first analysis on the original 100 participants, you got a p-value of 0.06, you'd be expected to be about half the time that with the new 100 participants, you would still conclude that your results were non-significant. But I think it's really interesting that if we did this, but we started out with an initial p-value of 0.01, something that we would consider to be statistically significant, about a third of the time with a complete new set of randomly selected participants from our population, about a third of the time we would end up with a non-significant result, which brings into some considerations about replication of a study. So while sample size is absolutely important to your analyses, there is no guarantee that by increasing your sample size, you'll obtain a significant result in either the reanalysis of the data or in a repeat experiment. A few other considerations, I've got p greater than 0.05, but some of these also relate to p less than 0.05. So a few other considerations related to, they're related to questionable research practices. I'm only going to mention a couple, but this is a topic that will likely be discussed in future Explore sessions that will be presented in much greater detail. You could probably give an entire presentation on each one of these points that I'm going to mention. First is related to p-hacking. It's also known as data dredging. So it's a form of publication bias. It's also reported as an inflation bias or selective reporting. And according to a paper by Head and others in 2015, they say it's the misreporting of true effect sizes and occurs when people are analyzing their data and they try out various analytic methods or data inclusion exclusion rules and only report those that lead to significant results. And it can come up because of a number of reasons. It might be it might be because you're conducting analyses partway through your data collection, you end up with a significant result, and you end your data collection because of that. Maybe you're collecting many variables on participants and only reporting those that give significant results. Or maybe you're changing the parameters of the analysis partway through or after your analysis. Something that's related to p-hacking data dredging is harking, which is hypothesizing after the results are known. So yeah, very much an extension of p-hacking where perhaps you run an analysis and you get an outcome where the results don't support your hypothesis. So you're not able to reject your null hypothesis. You might get into a situation where you think, well, what if I change this parameter, or what if I modify the hypotheses? This is considered a questionable research practice because you've seen your results and now you're creating new hypotheses, you're informing new hypotheses based on the previous results. Another consideration is, or something to think about would be the file drawer problem. This is another publication bias, and it centers around not reporting significant findings in publications. So you've performed a study and you end up with a lot of non-significant results, and they only go as far as SPSS and they never make it any further. They're never published in the literature. And what this has done is led to a large bias in the literature of significant results, and it's only telling half the story, really, for all the studies that are doing this. And another extension of this would be cherry picking, which you're just reporting some analyses that support your study or make your study look more significant than it is. So I've presented some considerations for situations where p is greater than 0.05, less than 0.05. You think about type 1 errors, type 2 errors, effect sizes. Is my data trending towards significance? What about p-hacking? So you might be thinking like, well, there's considerations both ways. What do I do? How do I navigate this? So we know that p-values can be misinterpreted, and measures like effect sizes aren't tied to having small p-values and aren't necessarily even reported. And because of issues around misinterpretations of p-values and null hypothesis significance testing, some calls have come for the elimination altogether of null hypothesis significance testing. And in fact, some journals have completely banned the practice outright. One example being Basic and Applied Social Psychology, which I'll talk about in a minute. So these bans and calls for ending null hypothesis significance testing typically lead to suggestions to only report effect sizes and confidence intervals in the place of a p-value, along with many other suggestions. Some say we can keep null hypothesis testing, but we should lower our alpha level from 0.05 to something smaller. Or maybe we remove an alpha level altogether and we just treat p-values as a continuous scale and we just interpret them that way. So there's a lot of thoughts and opinions in the literature right now. But my question is, and something that I'm still trying to grasp and rationalize is dropping null hypothesis significance testing a good idea, a realistic idea? So, what if we never ran a t-test again? What if we never ran a chi-square test again? There are other journals as well, some large journals like the New England Journal of Medicine that do have new guidelines for statistical reporting in their journal. So that gets to the idea of is this realistic? I think it is. Researchers will tend to adapt to the guidelines as needed in order to publish their research findings. And the New England Journal of Medicine made a statement that said they have a requirement to replace p-values with estimates of effects or association and 95% confidence intervals when neither the protocol nor the statistical analysis plan has specified methods to adjust for multiplicity. So that goes back to the multiple comparisons that I was mentioning. So I think it is realistic that we can move in a new direction for our statistical analyses. Whether it's a good idea, I think, is still up for debate. If we return to the Basic and Applied Social Psychology Journal, I believe it was in 2014 that they banned the practice of null hypothesis significance testing. So a few years later, Fricker Jr. And others, they assessed the analyses that were performed in 31 studies that were published in Basic and Applied Social Psychology after the ban on using p-values. And what they ultimately identified were numerous times where the results and conclusions of those studies were overstated and were overstated past what would have been concluded if they just used null hypothesis significance testing. So it almost appears like in that case that we've gone from one misused methodology to another misused methodology. So I think there's still a lot of debate that's out there, and still room for consideration about how we can improve the statistical analysis and quantitative data analysis that we perform. So what should I do then? Well, my first comment would be, or my first suggestion would be, to be cautious and transparent. So be cautious when you approach the interpretation of your results following statistical analysis. And being transparent in your research practices helps eliminate some of these questionable research practices and really details the process that you've taken with your data. Planning a data analysis plan ahead of time and sticking to that plan is really the ideal strategy. Extending from that comes a suggestion to use more than p-value to draw your conclusions. Being mindful that the p-value only tells a part of the story for your data, with a lot of different factors influencing that p-value that you obtain. You should always report your effect sizes with confidence intervals. They give more context to your results and can be used in conjunction with your p-value to provide a better sense of the effect that's being seen. And I know I just mentioned this, but I'll mention it again, and I'll leave you with this. Being mindful when you're designing your study. This is your opportunity to plan a robust study that can eliminate many of the considerations and concerns that I've detailed here, or take them into account. So I'll use that as a little plug to highlight our department does accept research consultations. So if you ever have questions about designing your research study and how to be more cautious and transparent with your data analysis plans and how to approach some of the things that I've talked about, please reach out to us. And I'm happy to take some questions or start some discussion. listed my email here, but we'll just move to one further slide with some resources and some things that I've used to design this presentation with my email in the top corner there. I'm happy to